Hi, everyone. I'm Brian with the Scientists in Every Florida School program. And in this edition of Science Segments, I'm excited to connect you to a scientist to help you learn about astronomy. What is your name and title?
Hi, my name is John Della Costa. I'm an astrophysicist and researcher at Florida Atlantic University.
What do you research and why is that important?
So I actually study the very centers of galaxies. We think that at the very center of every galaxy in the entire universe, there is a supermassive black hole. These are black holes that weigh over 1,000,000 to 1,000,000,000 times the mass of our own sun. And I studied what happens when matter actually falls into those black holes. So when a star comes too close to a black hole, a supermassive black hole, or a gas cloud or dust cloud comes too close, it starts to spiral in what is called an accretion disk. It forms an accretion disk, which kind of just looks like a big whirlpool falling into the black hole. And as that matter actually falls into the black hole, it heats up and emits light. And I actually study the light coming from these accretion disks. That is important because if we can understand why and how much light is coming out, then we can better understand the black holes. And if we better understand supermassive black holes, because supermassive black holes make up the backbone of galaxies, and galaxies make up the backbone of the universe, we can better understand how black holes formed and therefore how the rest of the galaxy evolved from the very beginning to where we are today. So that's why it's important.
Can you briefly describe how people can predict how the initial mass of a star determines its evolution?
Yeah, so I actually love this question. I'm a pretty visual person, so I brought a few models along today with me. But basically, the initial mass of a star tells you what's going to happen to it when it dies, when it's at the end of its life, what's going to happen to it. So basically, the bigger the star, the faster it will go through its life, and the smaller the star, the slower it will go through its life. So, and that is because it's kind of counterintuitive because you think a bigger star might have more fuel to fuel the fusion that's going on at the core. But actually, if it has more mass, more fusion is able to happen in the core. It's kind of like a race car or a drag car going down the strip. It can go really, really quickly and really fast for about half a second. And then you can't drive it any longer. Or a tiny star, it's like an electric car. It can drive for miles, hundreds of miles, and you don't even need to refill it up. So that's kind of the difference between these two. So let's imagine that the sun was the size of this NASA golf ball here. We can compare all the other stars to our star because we know it the best. We know the sun the best. So this star right here is very, very tiny, which means it will live for a very, very long amount of time. Our star is fairly average. It will live for about 10 billion years, where this tiny star will live for over 60 billion years, okay? It will live for 60 billion years, and when it dies, it will turn into a planetary nebula because it does not have enough mass to turn into a supernova when it explodes. That the same thing will happen to our own star, the sun. When it dies, it will turn into a planetary nebula, and it doesn't have enough mass to explode into a supernova. The next biggest star, you just call it this tennis ball here, this star will live for about 1 billion years. It's not much bigger, but it lives a lot shorter of a lifetime, a tenth as much. This will live for about 1 billion years, where the biggest stars that we know of, like this basketball here, these stars they only live for about 100 million years. And when they die, they turn into a supernova because they have enough initial mass. They turn into a supernova. And what will be left over, instead of planetary nebula for these smaller stars, there will be a supernova remnant that will be left over at the end of its life. And at the very center of that supernova remnant, there will be a neutron star. And if we even have like a bigger star, like a beach ball sized star, then that star will actually, what will be left over instead of a neutron star will be a black hole. So these turn into a planetary nebula and white dwarfs. This type of star turns into a supernova remnant and a neutron star. And the even bigger stars turn into supernova remnants and black holes. So that's kind of how, it all depends on how much initial mass you have. And that will determine if you'll die in a really cool explosion or just kind of let your outer layers of the star go. Be fun.
Thank you, John, and thank you all so much for watching. We will see you next time.